Thank you for the nice introduction. Welcome. It's a great pleasure for me to be here in Bern. It's been a while since I was here the last time. As you just heard, today's session is about fraud detection in financial services using graph analysis and machine learning. Safe harbor statement applies. That's the standard statement you always see from Oracle. Never mind, I'll be talking about things which are available as products, with the exception of one thing, which I'll explicitly mention. So other than that, this is my license to lie, right? Don't believe a word that I say. I may be telling complete nonsense, and this is what allows me to do this. No, just joking. So graph analysis. Just one thing up front. When I say graphs in fraud detection, I am not referring to graphs as in bar charts or pie charts and things. I am referring to graphs as in social networks, for example. Here, this is a little piece of my social network, which has been extracted from Twitter, right? So if you want to tweet about my session, right? My Twitter handle is Spatial Hannes, which is the one in the middle, and you can see who I'm connected with, who am I following, who is following me, and so on. So that from graphs, already by looking at it, you can derive some information. You would see and find graphs quite a bit in social networks, obviously in social network analysis, but it is a very generic concept. And what I noticed over the course of today was that there is a lot of buzz around machine learning, neural networks, deep learning, and the like here at the conference, but not so much around graphs. So I think it's a nice complement, what I'll be talking about, hopefully. In any case, as you've taken the decision to join me in this session here, if you're looking for a career in this domain, maybe you've taken a good decision to come here, because Gartner just said a couple of weeks ago that among the top 10 trends in data and analytics, one of the trends is graph databases and graph analytics. And there is a significant shortage in expertise. So maybe you can take away a couple of things from this topic, which you can then put to better use in your professional environment. Right, so as I was just saying, graphs are usually associated with social networks, but the concept is very general. Just out of curiosity, who has been working with graph databases, graph analytics, maybe by show of hands? Okay, there's a few here and there. It's not as, okay, I would have thought maybe a little more. Okay, so just so that everybody's on the same page, graph databases or graphs in general are a means of representing basically anything where you represent entities as vertices and the relationships between these these vertices as edges, right? Some people talk about linked data here. As I said, you would find this in social networks. You would obviously also find this in physical networks, but in the domain which we're looking at, it's probably a better approach to also look at knowledge graphs and the like, and you'll see what that means in just a moment. So graphs, as I was just saying, or as Gartner was just stating, have become very popular because they make data modeling very easy, right? You have a flexible data model, you have no predefined schema, or you have schema on read, if you will, and already from graphically representing the graph in a sort of visual manner, you can derive information. But the key thing about graphs, which also makes it different from relational technologies, is that you can run different kinds of analytics, which in the relational world is either cumbersome to code or slow to execute or impossible to run anyway. So that's the big advantage of graphs. And just to give you an idea of what our customers are doing with this, people tend to use this in a variety of areas, like to identify influential customers, influencers on social networks, and so forth, or looking for patterns which are dependent on relationships, or quite a few people also use that for recommendation engines and so on, where traditional approaches sometimes reach limits. And graphs are a very powerful and compact way of representing this. So to move to the examples, which I briefly wanted to touch on, what customers tend to do, or the main domains where we see graphs being applied are, for example, in public safety, in retail, and in financial services. And I was specifically focusing on financial services in my talk, because there you can see very nicely, just by looking at the financial transactions between accounts, how your customer base behaves. And you can look for similarities, you can find anomalies. And this is one example which we did with Banco de Galicia, which is sort of part of a bigger big data project, where they use all financial transactions which they have in their systems to identify what they consider to be undesired behavioral patterns, specifically looking at corporate customers who are kind of misusing the bank for just the low profitability services while banking with another bank for other things. Right? That is what they try to identify in this space. And already by looking at the patterns as you can see them on the screen, they can identify behaviors, financial transactions which, for example, reach their bank from another account which has the sender, where the sender is a corporate which normally banks with Banco de Galicia, and identifies those as, they are using other banks for other services. And they actually go after these customers. They increase fees, they sometimes even, up to the point where they terminate contracts and so forth. Now that's one kind of pattern analysis they do. Another example which makes this maybe even more clear is what we're doing with PaySafe. PaySafe are a provider of online payment solutions. So they have e-wallets. Maybe you've come across Skrill as a term or as a brand, which is one of theirs. They actually generate quite a large amount of revenue, and they have around about 500,000 payments per day running through their systems. And as you can imagine, these online payment providers, particularly these e-wallets with small amounts of data and so on, they are very popular among fraudsters. So one of the key things which PaySafe are trying to do is to use the infrastructure they have to identify fraudulent behavior. And they've come to the conclusion that there's really only one way to effectively do this above and beyond what they use already as a rule-based approach, which is to use graphs. And they use it both in real time, so when the actual transaction happens, as well as during account creation, trying to figure out if somebody is associated to someone who is associated to someone who's on a blacklist or something. So they do analytics by means of trying to identify transactions which exhibit behavior which is not desired. And you can see on the left-hand side one example where maybe the yellow dot is a betting site, where you have a limit of, say, $10 per bet. And if there is someone who wants to invest more per bet, who wants to bet more on, be it a soccer match or whatever it may be, sometimes these folks, they just create 40 or 50 or 60 additional wallets and then spread the full money, like $4,000, to all of these other accounts, and then bet on this one betting website. So that obviously is an undesired behavior, which they want to identify, which here is not so complex. But if you look at the right-hand side, this is one typical case where a fraudster is trying to bury suspicious behavior in lots of transactions, right? You create lots of accounts, lots of wallets, and then you obfuscate what you're doing by transferring sometimes only small amounts of money, but in a large number of transactions between these accounts. And then if you look at that more closely, you'll find that there's only one source and only a very limited number of sinks where the money ends. And this whole scheme is obviously just designed to hide something. And that is exactly the kind of thing which they try to figure out in their database. If you try to do this kind of analytics on relational technologies, you'll have a very hard time, because you'll end up with a lot of joins over joins over self-joins over joins, which are possible, but may take a long time to run, particularly if you have a huge amount of data coming in all the time. So these are the examples where our customers are using graph technologies already in an interactive manner, or during the financial transaction when they match the incoming and outgoing account against their transactions graph to figure out if there is, for example, a fraudster within so many steps of the target account, just to use one example. At the moment, they are using a rule-based approach for identifying fraudulent patterns, plus they have this interactive approach where they are trying to find out from the transactions which ones would be starting points for suspicious behavior, and do manual analytics from there. What they're moving towards is to extend that with more machine learning. And one signal which goes into the machine learning which they're already using is, for example, the fact if there is a convicted fraudster within so many hops of the target of the payment. That would be, for example, a strong signal. They are increasingly moving towards combining the graph analytics with the machine learning. And the rest of my talk will be focusing specifically on that topic. Before I move to that, I would like to briefly, because not everybody is so familiar with the topic of graph analytics, I would like to briefly go over how you can do anomaly detection with graph databases or graph analytics in general, just to give you a feeling of how this works and what is possible. And the example I'm using is not financial services related, but it's easy to abstract in the sense that the approach is kind of similar by means of looking at the same kind of pattern. What we've been doing in this use case was to try to identify anomalies in healthcare billing data. And what we did was we modeled the healthcare billing or the healthcare activities in such a way that on the left-hand side you would have all the medical service providers, the doctors basically. On the right-hand side you have the services they provide, and whenever a doctor was performing an operation or was delivering a service, we would create a link. So we would end up with a huge graph which is bipartite. You have doctors on the one side, you have operations on the other side, and then you can look at which activities, which services are close to which doctor, right? So this concept of closeness is a very important one in graph databases and graph analytics. In its simplest form, it can just be represented as the number of hops you need to take to get from one doctor to a service to another doctor to another service to another doctor. That already gives you a metric for how far away one doctor is from the other. Now, the idea for the anomaly detection here was to use this aspect of closeness to find those services which a group of specialists usually performs, and then try to find those specialists who do other things normally, right? And that would be sort of considered to be an anomaly, right? And graph theory to the rescue. There is an algorithm called the personalized PageRank algorithm, which exactly helps you to find these kinds of outliers and anomalies through graph analytics, basically, right? Those of you who are familiar with, or who are not familiar with the PageRank algorithm, PageRank is the algorithm which Larry Page developed originally to return the search results of the Google search engine. And it does not only reflect the number of connections to a web page, the number of links to a web page, but it also takes into account if a page is connected to an important page, right? So it's a recursive type of approach. Now, this personalized PageRank algorithm can be used very nicely to derive closeness in the way which I just tried to explain, to derive closeness from a given starting set of vertices. So if we go back to the example of the doctors, right? If we have a set of doctors that belong to one specialty, let's say neurologists, then we can look at, by means of the PageRank algorithm, or personalized PageRank algorithm, we can find out which other doctors are close, in that they are closely related through many similar services. That is the underlying idea, and the way this is implemented is you basically do a random walk, and then you do a random walk along the graph, follow the path of the graph, many hops. Whenever you touch a vertex, you add to a counter, and at an arbitrary point, you jump back, do that again, jump back, do that again, and so on. And from that, you can get a metric which reflects this closeness as a number which you can then make use of, right? And we have used that with a couple of refinements to identify outliers in that data set. And just for the sake of completeness, one outlier which we found was there was a gastroenterologist who was performing eye surgery, which sounded a bit, I mean, there may be good reasons for that, but I found that a bit odd. The way we came across that was we looked at all eye doctors, basically, right, all optometrists, and we looked at what are their specific tasks, what are the specific actions, and then try to find other specialities where somebody was performing one of these specialty tasks from that. Right? I have a more comprehensive explanation here, but in the interest of time, I think I'll leave it at that. If you're interested in a more in-depth discussion on how this works in detail, because we've done a couple of refinements here, then feel free to join us at the booth just outside, where my colleagues from the Oracle labs will show you a little demo if you want. So that's how to find anomalies in graph data sets, even without any machine learning. And so that's got nothing to do with machine learning, but you can combine it with machine learning. Because, as you probably already guessed, the metric which you can derive, this metric of closeness, for example, or there are other metrics which you can use or which you can derive from a graph, that can be an input to any kind of machine learning, right? You build your predictive model on top of that, run maybe your neural network, and maybe even feed back the result from your classification in the neural network back to the graph, where maybe you do more interactive analysis or further graph analytics or whatever. This kind of round trip can be very powerful because you get, and that's what I'll touch on next, you'll get different results from conventional sort of machine learning neural networks and graph analytics. To sort of bridge the gap between graph analytics and machine learning, the key question is, how can I reflect a graph in such a way that I can actually feed it into my machine learning infrastructure? As I said, one approach can be closeness, right, which is just one individual metric per vertex. But you could actually generalize that, trying to reflect the topology of the graph, so the graph structure essentially, as an n-dimensional vector, which you can then feed into your favorite neural network platform or whatever it may be. Right, and for that, there is an interesting approach which has been described in the literature and which has been implemented in a number of products, including ours, which is called deep walk, and it is basically using techniques from natural language processing as a basis in combination with random walks. And the way this basically works is, if you have a graph structure, like on the left-hand side here, you can generate, again, like in the case of the personalized PageRank, you can generate random walks. These random walks of a certain length, you can reflect them. They would be like, sentences in a Word document consisting of individual words where every vertex would be reflecting a word. And then you can use existing algorithms like word2vec to convert that into a vector. And that is actually an approach which gives you pretty good results. And let me try to explain that to you again with a little example. We had a sample data set from a university, and the idea was to derive which student was taking which course, or was taking which major or belonging to which department, just by looking at which courses is he or she taking. And I mean, again, it's not a it's a very generic type of use case. You can easily convert that to a customer segmentation problem, for example, or anything related to that. And here you would see, again, a bipartite graph, as I was already showing in the case of the medical fraud detection, where you have students, some of which are labeled, like computer science student taking these courses, a mechanical engineering student taking those courses, and so on. So with that, we would have a graph, and we were looking at how much information, how easily can we derive information from that graph by means of graph algorithms, in that case personalized PageRank, and what can we derive by means of neural networks. So we used a convolutional neural network, trained that on standard features which we derived from the information we had. That was like the student age, the gender, the courses. From the courses, we also looked at the course description. So we did some sort of more sophisticated natural language processing on the course description, trying to figure out key entities and so forth. Trained a neural network and tried to figure out, if I have a student associated with these courses, which is his major, or which department does he belong to? And then we did the same exercise with no neural network, just looking at personalized PageRank, and looked at the results. And the interesting output was, if you have the personalized PageRank, that's what you see on the left-hand side, the blue line, that already gives you an accuracy of over 0.7 just by running the algorithm on this bipartite graph, which I was just showing. If you compare that to the neural network approach, then, first of all, of course, you need to train this, right? And even after like 150, 160 iterations, the accuracy still was just over 0.5. Now, why is that? If you go back, then you can already see that if you have the relationships between the students and the courses, like here, for example, the neural network knows that this student is associated with that course and he is associated with that course, as opposed to the graph algorithm, which takes into account that this student is connected to that course, to this student, to that course, and that student has a similarity, even though there are different hops in between. And that is that's an information which is missing in the neural network. So graph analytics can be a very powerful tool that complements your machine learning in that sense. And if you start to combine this, like in this approach which I was briefly illustrating with the deep walk, then you can actually improve the accuracy of your neural network. But even if you combine the neural network with the original and the graph features, then you would only get slightly above 0.7 as the output accuracy. So it shows how accurate graph analytics can already be without any machine learning required, right? I hope that was the key thing which I briefly wanted to explain here in the few minutes that I had. So just to wrap up, I hope I've given you an idea that graph databases and graph analytics can be very powerful tools which complement conventional relational databases. They are especially strong in those data sets where you have connectivity. involved, where relationships play an important role. We have a couple of technologies which we can offer you, and we'll be very happy to show you more on our booth. Our team from Zurich is here all day, and you can even get a voucher for $3,500 worth of cloud credits if you want to try this out on the cloud. Right? Thank you.